Thank you for joining Once Changing the World, India's first Future Tech Meets Sustainability podcast. And today, I'm delighted and honored to have with me Professor Sriram Natarajan of the Department of Computer Science at University of Texas, Dallas. He's an Hessian AI Fellow at TU Darmstadt and a Robert Bosch Center for Data Science and AI Distinguished Faculty Fellow at IIT Madras. His research interest lies in the field of artificial intelligence with emphasis on machine learning, statistical relational learning and AI, reinforcement learning, graphical models, and biomedical applications. Professor Natarajan recently was elected as a Fellow of the Association of the Advancement of Artificial Intelligence and is recipient of many awards. So, Professor, really appreciate you taking time and being part of the podcast. Want to start with your thoughts on these large language models, because there's been papers showing reportedly talking about its emergent properties. Then there were papers dismissing the emergent properties, saying they are just mirages. And then recently, Anthropic shared that their models are faking alignment. Is there anything that has surprised you about these statistical large language models?
Anything that surprised me. Okay, so I think that's a good start. So first is that when they came out in the beginning, I was very skeptical because of the fact that they had to be trained on such large databases and stuff. So I wasn't very sure that, they got the nitty-gritty details right. So what has surprised me is how good their linguistic abilities are. I mean, they are conversing better to the point that when you talk to a large language model, it's very hard to distinguish whether it's now a human or a language model that is conversing. So they have really pushed the boundaries on language, on linguistic analysis. I think a large language, particularly in English, not all the other languages, but particularly in English, they have pushed the boundaries. So to me, what was surprising in the beginning was how well they were performing continuously on these language tasks and how robust they have been on language problems. So I think that's been the biggest surprise for me. It was the ability of these models in the beginning, right? And now once we understand how they work, and at least at a higher level, and how about their ability to carry out conversations and answer questions on a wide range of topics. And one of the particular thing that I'm very impressed by these LLMs are how well they can summarize concepts, right? So if you, for instance, ask them for a succinct summary of a large document, I think they kind of hit the nail on its head, because they kind of get you the exact summaries that you need out of these, research papers, or even for that case, clinical papers. Sometimes I take a clinical paper, I feed it into LLM to see what the summary is, and they're pretty good at doing that. And from what I hear from many of these, right, if I give you a good English description, they can write solid code, and that's pretty good. And I think those are all things that I've been pleasantly surprised by over time. Let me put it that way.
Right. So, Professor, what are your thoughts on the scaling hypothesis? Because there are people who believe that just scaling data, compute, and possibly some algorithm alone might lead to what we call these generally purpose machines, artificial general intelligence. What are your thoughts on something like that?
Can I maybe first address the second part, which is the AGI part? Machine learning algorithms, with many of these learning algorithms, with robotics, with reinforcement learning, with any of these set of algorithms, you have a clear, precise definition of what you are optimizing and what your goal in the end is going to be. The definition of AGI is unclear. This is unclear, right? And when you have something like that, you can't evaluate it, right? Unless you can evaluate something really well, there is really nothing that you're going to measure the performance on. So to me, that is a bigger peeve I have with this hype about AGI, right? And if somebody comes and tells me, well, AGI means we are doing better than humans. Well, that's not a bar. I mean, anything that flies 5 feet is better than a human. Anything that can, run faster than a human is better than a human. So having something better than a human is not a great bar for many of these problems. In fact, in many problems, we are already better than human. We can play chess because of the fact that we have this giant thing. We can play chess almost better than human. We have now AlphaGo and AlphaFold right now won Nobel Prize because we can do these things with large things. So for me, this AGI is something that I have not been bought into. What I'm really bought into is the fact that we can build these specialized algorithms that work very well on specific tasks. AlphaFold is a classic example. So if you ask me about the scale, and I like the question really because this is the most pertinent question at this point, is the idea of scale enough. For some problems, yes. And I say that very clearly. For some problems, yes. If I'm figuring out an image classification task where I'm looking at an image and saying, is this an animal or is this something else, a car or an animal? Or is this a UFO or a bird? Maybe scale is all I need, right? But if I'm going to do some other sensitive tasks, a rare disease prediction, predicting the mutation of a particular gene and its effect on a particular disease, scale is probably not enough at that point. So those problems require deeper synthesis, careful analysis of algorithms, rather than saying, oh, I'm just going to throw all the data that I have into this algorithm and then get it to work. I always, 10 years back, I used to give this talk in which I had this slightly controversial slide where I said, big data is a sham. Okay. And the point I was trying to make was, it's not the big data that matters. It's good data that matters. And the same thing goes for scale. I mean, just because you have scale doesn't mean it's going to do well. You want good data. Even now, good labeled data is important. Let's take the chat GPTs and Geminis and other stuff. They gave racially insensitive answers. They gave sexually insensitive answers. They gave very inappropriate answers back when that happened. You really think they went back and fixed it by just retraining? No. Somebody sat there, fixed those mistakes. So the human intervention is extremely important in these tasks. So for me, scale is not everything.
Right. So, Professor, I mean, do you think that you would be able to kind of define AGI? Because, you mentioned that here just maybe being better than human does not matter, because, at this, when this all started, we thought that the Turing test was the benchmark,
Right.
and then, it was overcome. We thought that, beating the world champion was the benchmark, overcome. Now we thought that maybe the ARC benchmark was the problem, possibly overcome. When do you think, because we're keeping on setting these benchmarks, and what's happening is that these statistical models are showing some really underneath the hood, doing something or showing something which we truly completely don't understand, because AI itself is completely a black box at this point in time. There are people who are working on interpretability and explainable AI, but people don't really understand what's happening behind the hood. Do you think you will be able to maybe define what AGI is from your perspective?
It's a very good question. I'm reminded of this first two things, right? So for all the viewers, if there is one set of talk that I think you should really see, it is this talk by Professor Tom Dietrich from Oregon State, one of my mentors. He has this talk that he gives everywhere, which says, what's wrong with LLMs and what we should be doing instead. And it's a beautiful talk. It's a very broad picture talk. I actually brought him to IIT Madras last year, and he gave a talk on the same topic in IIT Madras. He gave a talk in COTSCOM, the ACM conference last year in Bangalore. And so there he lays out everything. The reason I'm mentioning him is because this notion of definition of an AGI, right? He has a beautiful post that he posted in Twitter. I don't know if it was in Twitter or on LinkedIn. And essentially and I completely 100% agree with him. He basically says that the concept of AGI, which is essentially the system that can match or exceed performance, basically shares all the problems that the Turing test had. Right? Because intelligence, from the perspective of AGI, is completely defined from the terms of human performance, right? The most important AI system capabilities are things that the humans can do well, is what he said in that quote, right? And I completely agree with that. I mean, to me, that's the shortfall of this idea of AGI in itself, right? Because I don't think I'm going to have this AGI, which is a general purpose tool that can solve many problems. I don't know how many of the viewers of yours are going to be Lord of the Rings fans, but I love the book a lot, right? And in Lord of the Rings, the ring, there is one ring that rules them all. That's the one ring, right? And I don't think we are going to have that in AI. We are not going to have an AI system that's going to rule everything, in the sense that that's going to do everything correctly. What we are going to have, and going towards it, is futile, right? And instead, what I think we're going to have are systems that are going to do specific tasks perfectly, nearly perfectly. And that perfection is what we define in terms of the evaluation function, right? So if it's the number of defects in a car, then that's the right thing. If it's the shortest path from A to B, then that is the right perfect measure. So as long as you define a good optimization function and a good evaluation function, I think we can meet the benchmarks of those tasks correctly. In a reinforcement learning algorithm, I can do this reinforcement learning, and then this is the reward that I'm optimizing. Okay, great. Then you can get that solved and you can show that this works for that problem. But if you ask me, is there going to be a general AI system that can you define such that it's going to be meeting this AI AGI benchmark? First, I don't believe that such a system can exist, because there is no universal intelligence, as we call it. And I don't think we're going to reach that yet. LLMs are tokenizations. So they basically take this text that you have, they have the in-context tokenizations, they find the tokens that they have proof, they find the proof of it in the literature, and then they are summarizing it, right? Okay, so they are next token generators. So they are not universal knowledge machines. They are basically, I have an input, I have an output, and I read that and I give it to you. But on the other hand, I can imagine an intelligent assistant system that does scheduling for you, that does automatic, email, when you are working on a project, and then you say, you go hit compose, and then it pops up the email, but it also pops up whom you are sending to, what slides you want to attach, and maybe suggesting what the body is. For some tasks, I can expect that to work. And those are the types of knowledge workers that can be possible. But I think that what I really would like out of these AGI type systems is to make us all work only 4 days a week and take 3 days off, right? So helping workers being more efficient is much more important than thinking at the level of, well, can I have this all-knowing oracle that solves everything? So personally, will not want to define an AGI in a manner that is covering everything. I don't know if I'm evading your question, but I think my answer is I don't want to do that definition, because no matter what definition I come up with, I'm not going to be satisfied by it.
Perfect. So, Professor, I hope your vision of maybe like an AGI kind of a system maybe eventually would reduce our workload and it possibly augments us. So, I hope that we get into that world. Talking about the black box AI and the explainable AI, you've been working on Markov logic networks and probabilistic reasoning frameworks. How do these frameworks enable more interpretability and makes the system more robust?
It's a beautiful question. Thank you. So there are two ways to do this, right? So first, there's a class of, if you go back to the history of AI, and I'm giving this lecture for the students. If you go back to the history of AI, in the beginning, we had all these perceptron type systems. This is back in 60s and early 70s. And then Marvin Minsky and Papert, they kind of broke that perceptron by showing that there are classes of functions like XR that you cannot learn with these perceptrons. Then we had a whole bunch of other algorithms that came up, but many of them were like back propagation by Hinton and Eason. And then we had decision trees and ensemble methods and so on and so forth. Powerful learning techniques that kind of like build this layers of propagation of some sort. And then deep networks essentially just expanded that, right? So that's the neural way, the statistical way of learning. On the other side, in again, as a history lesson, AI was very popular because people were building these rule-based systems, essentially expert systems where you write these rules and then at reasoning time, you just see the data, make a prediction and you're good to go. And so this was catching on. Many people started deploying it, but then this started the problem of AI winter, and because they could not deliver as much as they promised. Now in late 80s, they started putting statistical models and symbolic models together. That field was called as probabilistic logic learning or statistical relational learning, because they were basically putting the symbolic models with statistical models. And then there was also another field which was essentially putting the neural models with the symbolic models. This was called neurosymbolic learning. What we are doing right now is this idea of neurosymbolic learning, where at the lower level, you have these neural operators, which are in some sense reactive. At a higher level, you have these symbolic systems, which are much more deliberative. So let's think of a very simple thing. Let's say tomorrow I'm planning that I'm going to come to India. So I'm from Madras. So let's say I'm going to Madras to meet my friends at IIT Madras. And that's my plan. Okay. So what do? At a high level, I'm saying, okay, book your tickets and then make a plan. and then that's it. Then I kind of leave it. So that's where my symbolic system does. It kind of breaks down the task and says, do these small things. Once the ticket is booked, once the thing is booked, then I have to get to the airport. So what do I decide is, okay, I'm going to leave 3 hours before to go to the airport. My brain doesn't quite say what is the route I'm going to take, what is the force I'm going to put on my gas pedal, how much am I going to turn my steering. Those are all very reactive things that I see a percept, I react quickly to it. That's what a neural model does. A neural model sees this perception, reacts quickly, and then takes action and keeps going. Then there is a deliberative aspect, which says, whoops, I ran a red signal. Maybe I'm driving too fast. I have to go slowly. Or, oops, I just missed hitting the car in front. Maybe I braked too late. Now, these are your reactive things giving feedback to the symbolic system that kind of tells you back what to do. So what we are trying to build are these two-level systems where at the higher level you can explain things. But the lower level is a neural model, but that can still be explained because the task definition came from a higher level. Because you have a semantic representation of what your problem is. No matter what you do, I can explain what you do in terms of what has been told to do. So for instance, it says the goal was to reach by 3 p.m. to the airport, Dallas airport. So that's why Sriram was driving fast. That's a very simple answer that you can deduce based on what the goal was, what the output of the neural system was, and why did that mapping happen. So one of the ways we are doing it, and this is just our way of doing it. There are many ways to do this. I'll come to those other things later because you asked me about what I do. This is basically what we do is we try to think of a task at a fairly high level, break it down to lower level subtasks, and then see if we can explain those policies that are taking place at the lower level as a function of what has been happening at the higher level. So that's one way. The second way is what people do all the time, which is essentially I learn a neural model and then I construct an equivalent representation of this to the symbolic model. Either a rule-based model, like you just said, MLN type stuff, or I could learn a small circuit or a small decision tree to explain what the complex neural model was doing. So it's where you're trying to kind of mimic the decisions that is taken by the neural model. The third one was basically how you can do local perturbations and say, oh, this is similar to this and the other instance. So it's like how a doctor would explain to you. You go to the doctor and you say, why are you giving me this particular, let's say I'm diabetic. I go for an injury and the doctor gives me a steroid. I could ask this question, why are you giving me the steroid? My A1C is, 7.2. And the doctor could say, well, I saw a patient last week or last month who had a similar situation. I didn't give him the steroid and he was in acute pain and that didn't help. So we will bump up your insulin, give you the steroid. So that's a simple way of explaining something that they have seen in the past. So there are these ways to do that, but I believe that the easier way to do this is kind of explain the decision in itself by extracting a symbolic rule from that. And that's, I think, what most people are doing. But my point is that maybe I'm stepping again backwards and say horses for courses. I don't need neural models for every problem. If I have 7 risk factors and I'm trying to predict an adverse pregnancy outcome, let's say that I know the blood sugar level, I know the exercise level, I know how the person is stressed out at home, and so on and so forth. There are like 6 things. And now I want to predict whether this person is going to have a preterm birth or a pre-eclampsia. Well, I can do that by building a smaller model. I don't need large models for this. So horses for courses is my way of thinking, which is one of the reasons I'm not a fan of this idea of AGI. You probably got that very clear, loud and clear from me. So for me, there are models that can be, so there is a beautiful paper by Cynthia Rudin from Duke, where she talks about, build models that are already explainable than saying, I'm going to build a complex model and then try to explain it. Right. But I think the truth is somewhere in the middle, in the sense that, yes, I agree, build a complex model, a smaller model, if it has good performance. But in some cases, like images or proteins, you really do need your large models. And in those cases, you got to figure out a way to explain them. So I think both ways of doing that are appropriate.
Professor, Agentic AI is in the hype cycle. Would you be able to explain Agentic AI? And besides OpenAI's operator, which are the other Agentic AI apps? And how do you get these multi-agents to orchestrate? And how much autonomy do you see these Agentic AI displaying in the next few years?
Yeah, again, right. So Agentic AI the idea of agentic AI has been around for a while, right? I mean, if you read Stuart Russell's book, the first chapter talks about agents and what are the types of agents, reactive and other types of agents. And there's a whole bunch of this, right? But now I think this idea of the agentic AI comes from the idea that you can do these types of probabilistic reasoning that is very highly adaptable to changing environments and stuff. Again, I think that this is going to be successful for some some specific subtasks. So if I define a certain set of tasks that these agents can do by itself, right? So for instance, I give you the code and then I give a definition of this problem, and then I'm going to let the system generate the code, but then give some instances for the testing and then figure out where the error is. And then maybe debugging can be faster when working with this agentic AI system. Or if I'm going to do a grocery shopping system, well, maybe I can just send this, exactly give what I need and what is the specification. Some people like, even in fruits, some people like certain types of fruits, the same fruit in the sense, like I like my banana not too ripe, not too this thing, but my wife likes it ripe. So for my diabetes, I don't like it too ripe. I like it a little bit on the other side. So you got to have these specifications, and the input criteria keeps changing. And as the criteria keeps changing, as the domain keeps changing, this robot needs to figure out what it has to do correctly to pick up the right fruit for the right person. So this, when the specification changes, these things adapt dynamically. And I think for many tasks, this is going to be useful. And I think things like planning a vacation, booking, booking your hotels and flights and stuff, I think can be automated pretty quickly, pretty robustly. But then we humans typically don't like to lose control. And those are the problems where we are going to have a lot of problems. The problem with the world is fully controlled by humans at this point, right? At least the environment is mainly controlled by humans, which means that the human error creeps in every aspect of things. And driving is a classic example. When do I think accidents will be minimized? If every single car is a self-driving car, then maybe we won't have accidents, right? Because we can figure out the intentions correctly. I mean, but here we have a fantastic way, right? You drive, you look at the eye contact, you make an eye contact, you know what that person is thinking. There is no verbal communication, there is no verbal cue, but just the eye contact, you know what is going on. Somehow that is not easily encodable in an AI agent, right? Because they cannot do that reasoning that we do, that somehow our culture, the way we grow up with, we kind of figure these things out. So there are some tasks in which agentic AI can be very successful. And I'm thinking those are all in a controlled environments where there is dynamic changes in the environment, but that is not so stochastic in the sense that it's not completely at random, right? It's not a human erratic behavior that's going to happen. But the domains itself can be dynamic and they can be adaptive. And I can see that in little bit in finance, definitely in, as I said, tourism. I think that could be one classic example. I'm hoping in assistance of elderly, managing their medications. I want to build AI systems that have deeper impact, right? So my parents are old. Can I remind them to take their insulin at the right time, the medicines at the right time? Or did they eat at the right time? Or did they call the helper at the right time? So those kinds of things I think needs to be automated, and they can be well managed by agentic AIs, right? Or I want to distribute medicines to a remote corner in India. Well, there is a way to do it right. You don't have to keep sending the same person back and forth. If you can figure out exactly a way to deliver this by predicting when these people need these medicines. So there are problems in which agentic AIs can have very, very high impact if implemented right. But then if you take the same giant large model and then say, I want to do this on every task, we are going to fail miserably.
Right. So, Professor, I hope that, make these models more utilitarian, and I think the world will completely change, narrow it down and find those exact use cases and make it work, whether it's embodied AI, agentic AI, these large language models. And they're already showing so many, really, really, very useful use cases. Wanted to get your thoughts on these open models as well as these proprietary models, because I think DeepSeek is in the news for the last couple of weeks because of the V3 model and the R1 reasoning model, which was the V3 was built. It seems that they're saying that was built just under $5 million. What does this what signal is this sending out? And would love to get your thoughts on this open versus closed source model. What's the future of these large language models or agentic AI?
You're talking to a computer science professor who believes in open sourcing everything. I don't have a single patent with my name on it. Every single that paper we publish, we push the code out, right? So I'm always of the opinion that open models is the way to go, because I think this kind of a technology can be enhanced and embraced by everyone. And which is one of the reasons I think that these DeepSeek models, particularly the R1 that came out, is quite interesting, because of the fact that you can train it with much, as you rightly said, much smaller budget than the $500 billion that they are trying to get from the US government. So for me, the idea of doing this open models is probably the right way to go. I agree with Jan LeCun on this, and there's been many people have been saying this for decades now, that many models have to be completely open. So for me, this idea of open models are going to be the right way to go. Having said that, it's also the reality that people are going to make it quickly as closed as possible, because if a company is going to take that open source model, figure out a beautiful use case for it, fine tune the model with the specific data that they have, they are not going to release the model, because sometimes releasing the model can reverse engineer and reconstruct the data. So it's the question of who do you want to benefit at the end. So sometimes closing the model is probably not the worst thing to do. So for instance, as a classic example, I built an insurance model which predicts I built a health prediction model which predicts what the, survival chances of a particular person is in the next 1 to 2 years. And if an insurance company gets hold of that model and reverse engineers it for that particular patient, they can make a exact prediction, and they can jack up the insurance rates. I mean, we are going to predict with a probability. It's not like it's going to be exactly the same, but then they're going to be more conservative and they're going to jack up the insurance rate for this particular individual. Is this societally fair? I don't know the answer, right? It's very difficult for such problems to be, we have to have a conversation, understand it, and then go from there. So for me, there is some value in making sure that some problems, some data are still not exposed. Like I'm a dad, so I don't want my kids' private information to get out, no matter what. So if there is an open source model where they can reverse engineer and generate a virtual kid who is exactly similar to my kid, then I don't want the model to get out, right? So there is that privacy ethics concerns that we have to worry about. But in general, I believe that research should be as much open as possible. So these open source models, particularly the ones that you just mentioned, are ones that are going to really be the ones that people are going after. There is a reason why many of the early LLMs are not that highly cited and followed now as they were a few years back, right? And so that's why I think that, open source models are going to be the way to go. And I think that those are the models that are going to really be the most impactful, if not anything.
Right. Yeah, Professor. Yes, I think the balance is the way to go. We live in a centralized world, top down hierarchical. And if we end up building these powerful machines, and if it goes into a centralized company, I think that it would not be. So I think, a balance is really, really needed in, building these machines, which possibly, could, pave the future of mankind. Can you talk about your lab, your statistical artificial intelligence and relational learning group, and the works that you've been, doing over there, which has been divided into 4 different groups: human allied AI, precision health, efficient star AI, and applications?
Thank you. Yeah. So as you rightly pointed out, maybe I'll give you a little bit of background, right? I finished my PhD working on intelligent assistants, essentially building these reinforcement learning models. But then whilst building these RL models, we realized that we have to get some sort of a domain knowledge in. So we went for this probabilistic logic models. Essentially, as I mentioned earlier, you have these rules that can be written in symbolic, and then you learn the parameters. Once you do that, we realized that these models can't scale during test time. During deployment time, they kind of break down. So there was another area of problem called as lifted probabilistic inference, which essentially said, can we reason as much as possible at a higher level before going down to lower levels? So for instance, let's say that I'm visiting again Chennai I actually am visiting in March, but let's say if I'm visiting Chennai, I'm not going to look at the weather in Australia. I'm not going to look at the weather in Singapore. I'm not even going to look at the weather in Kerala if I'm visiting Chennai. I'm going to only figure out that the thing that is relevant to me at that point is that area that I'm going to fly into and be there, right? So this kind of reasoning, we humans are very good at kind of doing it very well. So this lifted probabilistic inference, we kind of developed several algorithms that kind of only focused on the most relevant information to the query at hand. And in my opinion, developing algorithms for the sake of them were not very interesting. So we were motivated by healthcare applications. So I started off by looking at predicting side effect of drugs. If there is a treatment that they give, what are all the possible side effects. And then I joined a medical school just so that I could get my hands dirty on clinical data and actually work directly with electronic health records and other types of clinical data. So I spent like 3 years in a medical school trying to learn on several problems, predicting heart attacks, predicting early onset of Alzheimer's, predicting side effects of cancer treatments, and so on. And then we moved, and then the StarLing Lab, we started having this thing where 40% of our time is devoted to some sort of a high impact problem. Right now, we are looking at predicting adverse pregnancy outcomes, predicting neurological injury in children, predicting heart attacks in children who are admitted in hospitals. And so these are the problems for which we are extremely motivated by. We looked at the data and then we realized where is the gap in literature in terms of building a model. And then you write an algorithmic paper which kind of fills that gap in. So our work goes both ways in the sense that we build these statistical relational learning, probabilistic logic. Now it's called circuits, neurosymbolic learning, reinforcement learning plus planning type algorithms, but to implement them on healthcare data. So that's how our work has been in the last, I want to say 15 years. So most of my students will have two types of papers. One is an adaptation paper where we adapt one of our algorithms to a problem of high interest. And then one is a fundamental paper that is presented mainly to a computer science audience.
But Professor, so, when you talk about these predictive models, how does this work? I mean, is there like the data is collected, and you mentioned Alzheimer's or other conditions? How does that work? Can you elaborate on that?
Yeah. So for instance, let me go to a concrete problem: predicting adverse pregnancy outcomes, because we had a 5-year project that is just getting over, and we are trying to get it renewed. So it's a very concrete problem. So in this problem, what we have are about 3,200 women from Indiana, Bloomington, Indiana, and the Indianapolis area. And we have data on them as part of a clinical study. And we look at this data, and then we build predictive models to predict some side effects, right? So, for instance, we are building probabilistic models, Bayesian networks, probabilistic circuits, some boosting, gradient boosting. By the way, the readers should always try gradient boosting when they have tabular data, because that's one method that works beautifully on many tabular data problems. So gradient boosting, we try these models. And then we have our domain expert, and we speak to these domain experts. Dr. David Haas from Indianapolis is the one who's working with us, and we get knowledge from him. So for instance, we built a model, right? And let me give you an example. Our model simply said this probabilistic rule: the woman is highly educated, then the chances of having gestational diabetes is high, right? So it turns out that if the woman has a PhD, the chance of getting gestational diabetes is high. And we were shocked. I'm like, why would an educated woman have this? And we took it to the doctor, and the doctor started laughing, and he said, Shrira, in the population that we are looking at, the educated women are mostly on the older side because they are all professors. And so age is actually the reason why they are having gestational diabetes, not the education level. In your data set, there is a 1:1 correspondence between age and education. So we went back and looked at it, and he was perfectly right. So this is where the human allied AI comes in, because we make a prediction, we try to explain it to the human helps us understand whether the prediction is correct, or sometimes we fix things. So for instance, we also looked at BMI and gestational diabetes, but we looked at BMI and race. And this was something that was not well known. So some races, particularly the African American, BMI had a direct impact on gestational diabetes. Whereas in the Caucasians, the white Caucasians, they didn't have as much of a clear this thing. So this was found by us, that they were still not sure if it's true by human knowledge. So these are things that we augmented to the human. There are things that we got back from the human. So the way it works is in an iterative manner. Now, once we did this, we are taking the model that we learn and we are applying to an Indian data set called Garbini that has been funded by Indian government with my collaborators at IIT Madras. We are taking these models, applying it on Garbini data, and then trying to see if these kinds of models directly apply, what kinds of changes we need to make. And then now we are taking a third data set from another place. We are trying to talk to a cohort in Brazil to see if we can evaluate these algorithms in Brazil. And then we figure out that for India, for instance, they don't even measure gestational diabetes directly. So we have to take these other measures, find the influence, maybe have a gestational diabetes as some sort of a latent variable, and then go from there to predicting the other adverse pregnancy outcomes like preeclampsia, hypertension, neonatal stress, as well as preterm birth. Things like that we are predicting based on the refined data models that we build for India. So this is the kind of iterative loop that happens between building a model, presenting it to a human, reasoning it given on a new data, making changes, go back to the human experts, see if that data needs to be fixed, and we keep circling around this. This is the model development that we do continuously here.
AlphaFold came in, the AlphaFold model 2
Yeah.
and 3 completely changed the world with, the solving the
Yeah.
protein folding problem. What's the other areas, which you invested in besides these predictive models?
So I'm interested in the holistic problem of all the way from identifying and predicting a disease to figuring out what the treatment plan should be. So for instance, we are working with a bunch of neurologists and ECMO specialists here in Dallas. And we are working on figuring out should we put a kid in ECMO? When we put the kid in ECMO, what are all the possible side effects, which is the neurological injuries that we could happen, and how can we mitigate them? What are the interventions that we should get into, right? So, and so for me, the prediction is just one small aspect, which is giving me, in some sense, the probability of X given X. Y is the outcome. X is the set of things that I've observed. But then once I have this distribution, and then I have a utility function, what are the best actions that I should be taking? What should be the next step to avoid something even worse? If I know that somebody is at a high risk for preterm birth, at 16 weeks, when the woman is, at 16 to 18 weeks, I know that she's at high risk of preterm birth. What can I do to avoid her, giving birth before 35 weeks, let's say? How can we stretch out this pregnancy? This is what doctors do on a daily basis. Now, we want to figure out tools that argument, maybe, telling them that these are things that were taken in the other population that it worked. These were things that you tried earlier with somebody that did not work 7 years back. And so if you have a holistic understanding of the problem, we can develop these full-fledged treatment planning. So for me, it's always about action selection, and prediction is just one first step towards achieving that dream. So just going from prediction to action selection. The type of problems, I'm looking at neurological injuries. We are looking at the social impacts, right? So not every treatment is possible everywhere. We are also trying to understand whether some groups have put in more invasive treatments than the other groups, or why is there resistance? So even to vaccine, right? We are looking at some vaccine resistance. Why are some people resisting vaccines than the others? And in some cases, they have genuine reasons, and we want to understand them and figure out how we can, maybe address their concerns, or at least change the model so that we can understand that these are the people for whom vaccines do not work, and we should not do that. So things like this, we need to understand much more deeply. And so for me, those are the types of problems that we are working on. As I mentioned, cardiovascular health, Alzheimer's health. We are looking at the societal issues. We are looking at policy. What should be the public policies when it comes to health? What should be the health mandates? When are they correct? When are they not correct? The masks, for instance, worked, but is a mask mandate the right way to go? So things like that, we have to understand why they work when they work. And so those are the types of problems we are looking at. And as I said, prediction to action selection is the key thing that I'm looking at.
Right. Professor, you've been working on reinforcement learning. So what are the most promising applications you see for this technology in the real world scenario, particularly in the healthcare space of personalized medicine and precision health?
Right. So in the healthcare scenario, so first is that many people are saying robotic surgeries are classic way to do. And I think that's probably correct, but except that I don't know if it is fully automated in a RL sense, right? So I'm not going to say that that's the right way to go. But treatment planning is one where I can do reinforcement learning, because I can say that I can give you batch data of treatments that I've worked over the past few years, and I can kind of learn this idea of inverse reinforcement learning, where I basically look at these data, induce the reward functions, and then I can develop the personalized treatment plans for each of these patients. So that is where I think that the biggest application of reinforcement learning is going to be in treatment planning. So for instance, when Sriram walks in, and this happened like 10 years back, or no, 11 years back, and I give this example everywhere. I walked into an urgent care with a knee injury, right? And my wife was next to me. The doctor was asking me all kinds of questions, and I was on my phone because I was an assistant professor. I was waiting for some proposal result, something. I was very fidgety. And the doctor asked me, "Have you told me everything?" And I said, "Yes." And my wife, nicely gave me a whack in the back, and she said, "You have diabetes. You didn't tell him, right? I'm telling your entire audience that I have diabetes. So, it's not like it's a big deal." And so I forgot to tell the doctor. Now, the doctor was going to prescribe a short course of steroids for me. And then the system could intervene and say, "Doctor, he has diabetes. His last A1C is, actually, it's pretty much under control, but let's say hypothetically, his last A1C is 8.2. Do you want to go down this route?" And the doctor could say, "Oops, he didn't tell me that. Thank you for letting me know. I'm going to try some NSAIDs, see how he goes." we have this longer treatment plan. We'll go from there. Or the doctor could say, no, he's a severe acute pain. I want to bring the pain down. I'm going to give him a short-term insulin. So the system is going to interact with the doctor like a good virtual assistant would do, like a good, nurse assistant would do, by reminding the doctor of this. Or that you want the system to be able to identify what are the side effects, what are the later treatments that have come through, what is the new technology that's come through, because the doctors are not going to be on top of everything every single day. They have barely any time to see patients given the amount of healthcare stress that we are putting on. So I believe RL is going to be one of the most powerful tools in developing a virtual assistant for these doctors, so that the doctors can spend 10 minutes with each of us rather than going back and writing notes and doing all these things. 10 minutes with each of us in a more personalized manner, present them everything that is needed, every single alternative treatment, every single recommended treatment plan, and what are the success rates and probabilities of this working. So give them some more insight into the data. I think that's where RL is going to be very, very powerful.
Right. Yeah. So I think reinforcement learning, AI, leveraging with extended reality, I think is the future. I've been invested in augmented reality, virtual reality, mixed reality. And I think the future of healthcare and future of education, I think is with this convergence of these tech of sorts, because I think the future will be where you might not need to actually step out for the education of the healthcare. The healthcare will kind of come to you with these virtual healthcare and these digital twins, with reinforcement learning. So yes, I think exciting space, and these AI is now being more and more integrated into the healthcare space. Are there any ethical considerations you think that should be kept in mind with these?
There is always ethical considerations when we do these things, right? So first is the data cannot get out, right? There are some sensitive data so I have a family member, a very close family member, who actually had a heart attack 8 days back. And I got to know of it only 2 days back. This is a very close person to me. And why? Because that person is intensely private about guarding their outcomes, right? So we have to be very careful about these data privacy and the considerations there. Also, more importantly, we want to be just understanding that certain populations are sensitive to certain types of treatments. Certain populations, for whatever reason, religious reason, or their localized beliefs, and so on and so forth. We cannot have, again, that's one of the reasons I don't think wondering that rules them all is going to work. We have to have very sensitive, patient-sensitive treatment plans that go around. There is a human touch, right? That's why we call it humane. There is a human touch to this whole thing that we need to bring into these AI systems, make them deliberately aware of these kinds of issues. I mean, just stepping back a little bit, I'm pretty sure you have seen the Tamil movie was called Endiran. The Hindi version, Robot, was it? I think, where Rajinikanth was this thing. That was one of those beautiful movies for me, just from an AI researcher perspective. You have a scene in which this robot goes into a building with fire and beautifully protects the woman by taking her in a bathtub and bringing of course, I don't know which part of India has a bathtub in that kind of a community, but let's just say that he brings her in a bathtub out, but doesn't realize that she's naked and she hangs herself in 2 days. So this is the problem, right? It's not quite ethical there, but it is still the sensitivity aspect of the humans that needs to be taken into consideration. So robots are literal. AI is literal. They don't have this notion of the humane touch, other things societal things that we have. And I think when we build these treatment plans, these are things that we have to consider. There should be, first, no privacy things that are broken. Second is that they cannot have different treatments for different populations. We need to be ethically correct. I mean, if there are going to be different treatments, they should be conditioned on the local beliefs and local, their specific needs, that they have to be tailored, but not just saying that, race A is superior, they get this, race B is superior, inferior, so they get this. This kind of nonsense should never happen. So there are these other things that we have to be very careful in how we do. But here is my worry. The data comes from humans, and humans are inherently biased. We have our cognitive bias, our societal bias, our religious bias, our whatever bias we have infinite amount of biases as humans. And when the data that we create also are reflective of those biases. So if you are just evaluating the performance on the data that is biased in the first place, the system is going to be biased inherently. So this is an evolving process, in my opinion. This is where, as a community, we should all come together, try to remove our biases as much as possible and make this work. So for me, that's the dream. That's why we do what we do, in my opinion.
Right. You're talking about the entire evolution of human race, because yes, I think we humans are inherently biased, and obviously that reflects in the data, and I think that's a very, very big task of humans changing, because I think we live in a capitalistic world which is centralized, and there is so many things which divides us rather than unites us, and I think all the forces understands this, that the forces, the powers that be understands this, and they keep on working on that, keep people divided rather than united, with politics and religion and so on and so forth, and boundaries, these national boundaries, so yes, I think we humans have so many biases, and those are definitely kind of trickle down into these models.
AI systems, yeah.
Yeah. You, Professor, what's your intuit on building more powerful models or more maybe autonomous agents? I mean, what do you think could be like the things, if we kind of solve, we tick mark, could we could lead to like maybe fully autonomous agents?
So fully autonomous agents, I'm not even sure if that's possible, because of the fact that like self-driving, right? Let's just take self-driving as an example. I built a beautiful self-driving car that works beautifully in, let's say, in California, or for that case, in Dallas. It's going to be tough in Dallas because of how people drive. But let's say that you build that. You think that we take that and put it in India, it's going to work. The environment is going to change so rapidly that it's very hard to drive. I actually think that somehow for me, driving in Dallas is more stressful than in India, because in India I just look straight and I'm driving. Everything around me takes care of itself. In Dallas, I have to look here, I have to look there, I have to look here, and then I have to make sure that nobody merges, nobody does this. In India, I just drive, and people. Thankfully, I've not even had a single accident, because people around me, there is some order in the chaos that I see. But you cannot build a system just saying that this thing. So for me, fully autonomous systems are possible in some cases. In airport security, I can see that happening to be fully autonomous. There are cases like maybe plane scheduling and so on can be autonomous, subjected to all the security constraints. And if you have figured out everything right, personally believe, and actually maybe this is a shameless pitch to the most recent paper that I wrote. It's a blue sky paper at AAAI where I say automate or collaborate. Okay, and we have given you some examples. This is a paper that talks about whether AI is in the loop or a human is in the loop. And we are trying to say, understand first this problem of whether AI is in the loop or human is in the loop, develop correct evaluation functions, and then go for it. So if you want to automate something, so for me, some things can be automated. Some small things can be automated, where things like a prediction model can be automated. If I'm going to predict whether somebody walks in and they say, oops, this person is going to has COVID, without even doing the diagnosis. Or if this person walks in and I say, ooh, there is a 90% chance that this person is going to have a heart attack in the next 3 weeks. That's great. That's an autonomous system that works by just looking at whatever measures, like you just said, variables, the sensors, blah, 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 augmenting everything. We can do this in the minimally invasive possible. But then once we have that, I think the human has to come in to figure out what is a good treatment plan that works well with this human, because of the constraints that they have, because of the societal problems that they have, because of the pressure that they have. Maybe it's like my case where, the children are in the US. You just cannot quickly go through all of this until somebody comes there to help them out. So we have to plan everything correctly, right? I believe that's, and you should look at that paper, and I'm happy to jump in on another conversation, because that paper is written for a general audience, not just for the AI, right? So, so our claim is that the inner problems in these human AI systems can be automated. These are these prediction tasks. These are these regression tasks. These are the classification tasks. These kinds of things can be done automatically with some human inputs to guide them. But then once you have the decision-making system, that is where human takes control. So you have an automatic system that gives me the route to go, that plans my route, that tells me that take these highways. But then I have to take control and do the thing at the end. Same thing with treatment planning. Same thing with finance. Same thing with, I think we've given a bunch of examples, including education, right? I can set these questions for evaluation, but then every student has their own way of doing it. I want to understand what they are doing it. So it's more compassionate for me to talk to the person and understand, why did you think this way? What was your reasoning here? And then then give them a good grade than just saying my AI is suggesting this. I have an auto grader. This is going to be your grade. That's not the right way to do it. I think that, so that's why I think it's a shameless pitch for that paper, but I think that paper kind of nails it where your particular question comes in. So do I believe automation is needed? I think so, for some tasks, but I think that the human aspect has to be kept everywhere.
Right. Yeah.
So
Right, completely true. I completely double you on that. Professor, my last question to you. What's your moonshot? And will be great if you can leave us behind with a picture of a world you would like to see in the space of where AI converges with healthcare and, gives these real world benefits.
I think I kind of mentioned a few times, my moonshot is making everybody's life easier. My parents' life should be easier because of AI. My kids' life should be easier because of AI. Fewer distractions, get to the work when they are studying, when they work, a student, when they are in class, that we all have an attention span of 20-25 minutes. And within that 25 minutes, how to get that most important information correctly. For us, education perspective, that's where AI comes in. And that's where AI could be very, very valuable if we use it right. In a healthcare setting, when I walk into a doctor, I get my 10 minutes of the time with the doctor. I should not be repeating the thing that I just told the nurse. And because we are wasting time, we can have a conversation about where we can go next, right? I mean, you make an appointment. The nurse, whoever is taking everything down. And then you log in, you fill everything in. And then there is a nurse in the US, they see everything. They ask you the same. You go to the doctor, you're going to repeat it. Right? And that's waste of information. We are not doing things efficiently. Can we make it much more efficient? Can we make predictions so that we can make things we can improve the lives of people by, improving their efficiency at every turn point. So for me, a moonshot would be just saying that let's make life much more efficient so that we can do what we do today in 60 to 70% of our times, even 80% of our time. The rest 20% is freed up for spending time with family, with friends, to have relaxation, to have a better, healthier life. So that's what my moonshot would be, is to cut these efficiencies in every aspect of life, whether it is in healthcare, whether it is in productivity when it comes to work, whether it is in, driving when I'm going out. So things like this, where can we cut these corners so that AI can make human life better? Of course, my ultimate dream is to unite, right? I mean, like you perfectly said, they are dividing people in every single aspect. I mean, divisive is the only way politics is surviving. And I want people to get united, to maybe even see, no, in the end, all the blood is red, our bones are white. We are not that different. Come on. And we should be able to, hopefully AI would come out and teach us. Maybe no human can teach us. Maybe it's the AI that's going to show that these are the similarities and these are why we should not go for things. And of course, my worry is that when you do this, there are always going to be bad elements, right? So fire can use to light up a house or light a house. So it's both of them. So I think my moonshot is to make human life better as much as possible.
Thank you, Professor, for taking time and being part of the podcast and doing this fantastic work. Yes, I hope that we get into a world where the benefits of what you're building touches the lives of everyone, and makes a difference. Because yes, I think currently we do live in a very centralized world, and I see an AI arms race of sorts where we are, I think, all trying to build these powerful machines. And I think the end goals of all of these, whether it's these big organizations or whether it's these governments, is to acquire a technological advancement which will give you benefit or power over the other one. I hope that we understand we live in a world where we need to collaborate rather than create conflicts, because this technology is self-learning and it can create so much benefits. And the future is only going to be bright if we create collaboration, because conflict is only going to take us to a terrible path. So really appreciate you taking time and being part of the podcast. And to my listeners, if you like what you see in here, then please press the subscribe button. And until next time, see you guys. Bye. Thank you, Professor. Really appreciate this.
Bye. Thanks. Thank you. Bye.